Okay, so I'm going to finish up section 2.4 here. We looked at piecewise functions in the last video. The only thing left to finish up is the greatest integer function. So the greatest integer function is denoted by two brackets, and definition f of x equal brackets x means the greatest integer less than or equal to x. So suppose that we want to find f of 3/4. Okay, well, brackets 3/4 is not an integer. Okay, so I need to bump down to the next lowest one, which is 0, and 0 then would be my output. F of 2.5, f of 5/2. 2.5 is not an integer, so I need to bump down to the next lowest one, which is 2. Same thing with f of -1/2. -1/2 is not an integer, so I need to bump down to the next lowest one, which is -1. 2 is an integer, and brackets x means you want the greatest integer less than or equal to x. So 2 is an integer, okay, which means 2 is going to come out of that. Pi is not an integer, okay, and the brackets pi, well, 3, okay. Suppose that we want to graph f of x equal brackets x. Well, if I let x be 0, brackets 0 is 0. If I let x be 1/2, brackets 1/2 is 0. If I let x be 7/8, brackets 7/8 is 0. Okay, and if I let x be 1, 1 is an integer, so I get 1 coming out of that. Brackets 1 is 1. In order to make this a function, I need to have something that's going to pass the vertical line test. So because 1, 0 is, 1, 1 is on the graph, then directly below that 1, 0 cannot be on the graph. Okay, so I've got all these points from 0 to 1, not including 1, because 1, 1 is on the graph. And so 1, 0 is not on the graph. If I keep going here, brackets 3/2 is 1. Okay, brackets 9/5 is 1. Brackets 2, that'd be 2. Okay, so 2, 1 is not on the graph because 2, 2 is on the graph. So I want an open circle there at that spot. If x is 5/2, okay, well here's 5/2, we get 2 as the output. F of 3 is 3. Anywhere from 2 to 3, disregarding 3, would mean that I get 2 as the output. Okay, here's 3, 2, not on the graph, because 3, 3 is on the graph. Okay, this function also works for negative numbers. If x is -1/2, brackets -1/2 is -1. Okay, brackets -1 is -1. So you're always going to bump down to the next biggest integer unless that value is an integer. Okay, -1/2, -1, -1 is an integer, and anything that is between -1 and 0, not including 0, is going to put me at a height of -1. So I end up getting steps flowing the other direction. Okay, now the domain of this function is all real numbers because I can let x be anything I want, really. All real numbers. Now the range of f is all integers. So I only get an integer value coming out of this. 0, 1, 2, -1. Those are integer values. By the way, this is one reason why we call this the greatest integer function. Okay, it's because we only get integers coming out of that. Okay. Problem 31 on page 148 is a good one. It says in January 2016, the retail flat rate in dollars for first-class mail weighing up to 5 ounces could be computed by the piecewise constant function p, where x is the number of ounces. Okay, and so here's that function written. Oops. So part A, I want to evaluate p of 1/5. Or p of 1.5, and p of 3, and interpret the results. Okay, so let's see here. I guess let me begin by here's the function, and notice how this is an example of a piecewise function. Okay. I've got 5 pieces written, and so p of 1.5 is right here, 97 cents. So it costs 97 cents to mail a 1.5 ounce package. P of 3, well, 3 is in piece 3. 1.14. So it costs $1.14 to mail a package weighing 3 ounces. Okay. Part 2. Sketch the graph of P. What is the domain of P? Okay. Well, let's see here. So P of x is the price, which is 0.8, 0.97, 1.14, 1.31, 1.48. Okay, and x is going from 0 to 5. Now, if x is going from 0 to 1, and I'm not including 0, by the way, then it costs 80 cents to mail a package weighing 1 ounce. If x is 1 to 2, not including 1, it costs 97 cents. If x is going from 2 to 3, not including 2, it costs $1.14. If x is going from 3 to 4, not including 3, it costs $1.31. And if x is going from 4 to 5, not including 4, it costs $1.48. Okay, so you basically got a 17-cent jump at each additional ounce for mailing a package. And I've already commented on this, but the reason why I'm not including why I've got this break in the vertical axis here, P of x, is because I'm not starting the axis at 0. Okay, because of my conditions on P of x. You can have that if you want. I'm not picky about that, I guess. Although technically we should have it. If we want to know the domain of P, okay, the domain of P is 0 to 5, including 5. By the way, you can't mail a package that weighs 0 ounces. Okay. So x is strictly greater than 0, And this function is only defined for a package weighing up to 5 ounces. Okay. So let's see here. Part C, where is P discontinuous on its domain? All right. Well, discontinuous. Basically, wherever you're going to lift the pencil to go from one piece to another piece, you're going to have a discontinuity there. Okay, so there's going to be a discontinuity at 1, at 2, at 3, and at 4. You wouldn't include 5, since we're ending at 5. Okay, but at x equals 1, 2, 3, or 4 is where I've got a discontinuity. Okay. The homework in this section is on page 145. Be sure to look at these problems here when you get a chance for me.